All right, so right. I wanted to tell you about yeah, I mean Christina alluded to this a little bit, but some nice expression for mass. Um, so mm, well, okay. I don't know, a little preface is I made these slides with Google Slides and it doesn't look so good. It looks a little bit I don't know, grade school presentation, but bear with me. Okay, so yeah, if you I noticed there's some people that mentioned that they're not so familiar with these ideas, and so I would refer you to some texts here to get a maybe better well, I don't know, more full introduction to these, because I did not really have that in mind. But so Dan Lee has a very very nice book, the book on these ideas. So geometric relativity, take a look at that. And then also from the more mathematical physics side of things, Crucial has a lecture notes or lectures on energy in general relativity that I think is nice to, if you want to, get a little bit more from the physical side of things. Okay, so let me fix the setting and describe what we're talking about when we say mass. Okay, so we're looking at a three-dimensional Riemannian manifold, M3G. And then this is what it means to be asymptotically flat. Well, probably just these first two things. It means that there is some compact set omega in your manifold, so that upon removing, you can very nicely compare to whatever is left of your manifold to Euclidean space with the flat Riemannian metric. So in order to articulate that you say that, well, there's a little picture in the toy picture, and they have it right there. We say that, okay, there's a diffeomorphism, kind of a coordinate chart at infinity. Maybe you can write that down. Chart at infinity. It's referred to. Diffeomorphism from the complement of some compact region omega to the complement of a ball in Euclidean space. And now that you can, compare one metric to another using this diffeomorphism, coordinate chart, you could ask or talk about the difference between the two metrics, flat metric, delta, I write, and G on your manifold. And then the requirement is that should decay at some rate. And the rate is like the distance from the origin to the minus tau power, where tau is some number bigger than a half. And also the first and second derivatives of this difference between G and flat metric should decay as first and second derivatives of radius to the minus tau behave. Okay, the little toy picture here is, up here, you have a manifold. There's some compact region where there might be interesting topology geometry, but upon removing that, you are very well controlled compared to Euclidean space. And then for discussions about mass, we will need an extra requirement, which does not follow from this decay. If you think about it a little bit, you might realize that this does not follow from just having second derivatives that decay like this. But we want that the scalar curvature of our manifold is integrable. Okay, so a kind of extra decay assumption, you might say. Okay, so in this setting, you have this invariant called mass, which is computed at infinity in the following manner. It's also called energy, if you're thinking in a space-time context. This is pure Riemannian discussion here. Okay, it's this following limit where you are taking integrals over spheres, S R, in the Euclidean space, where you know what sphere radius R means. You can compute this integral of these first derivatives over this large sphere and take a limit as the sphere goes to infinity. And this, you might imagine, is some number. It's not quite clear if it's well defined, but it's an invariant of the structure that we have just defined, called the mass, ADM mass. some other vague ways of thinking about it. It's kind of like, well, okay, so first of all, it's, just to focus ourselves, it's like you're taking first derivatives of the metric and you're integrating them on some large, the boundary of some large region. It's not exactly that, it's more than that, but that's if you're talking about the order of things, that's the kind of the order at which mass is appearing. You could also think of it in the other following way, which is maybe a little more geometric, but also not very useful. But you can think of it as kind of, if you think of the scalar curvature map, given a Riemannian metric, you produce a function, a scalar curvature. If you take the linearization of that map at the flat metric in the direction of your general Riemannian metric, that's asymptotically flat, and then do a bulk integral of that quantity. That's roughly what mass is. So kind of integral of linearization. Generally said, it's some kind of way of, it's the boundary term if you try to integrate scalar curvature by parts. That's maybe one of the, if you want to give it a headline, that's what's one headline. Just to, because this is an introduction, maybe for some of you. I don't know if you're actually listening, but there's a metaphor. Okay, let me say a little bit more about mass. Okay, so in general in physics, if you have like a field and you want to construct invariance of it, if you have like a system, like a, some charged stuff, and you want to know what some electromagnetic field, you want to know what the charge of the system is. In the context of general relativity, you're studying a Lorentzian manifold, which is supposed to be a model for a gravitational system. And mass should be one of these invariants where you try to calculate, some kind of the total mass of the system. And usually this is done if you have a field by computing the flux. Like charge is like you integrate the flux of a current or something through some two-dimensional surface that encloses the system. And so how does this work in this metaphor? Or, how does that, how is this at all resembling what I just described? Well, there's a metaphor here. I'm going to put it in here, purple. And this is the metaphor over here. So loosely speaking, you think of the Lorentzian metric, H, as kind of like a gravitational potential. The Christoffel symbols, the kind of the first derivatives as the gravitational field. And then the Einstein tensor, this Ricci curvature thing that you see in the Ricci minus 1/2 HR is equal to 8 pi t Einstein equations. This left-hand side you think of as kind of like stress energy tensor of gravitational field. Now, obviously, if you know Riemannian geometry, this is very questionable because Christoffel symbols are not really a well-defined, they're not a geometric invariant. They depend on the coordinate chart. They're zero sometimes. But the point is, if you are working in the context like so of where you have a preferred coordinate chart, the asymptotic coordinate chart, then the metaphor that we're talking about here kind of comes into focus, and it makes more sense to say, oh, what I mean by the flux of the gravitational field through some large surface that's enclosing the region. And in that metaphor, if you follow it through, this is the formula that you would get for something that you would call the mass of the system. So it's kind of a vague metaphor that you can make a little bit more rigorous, but that's kind of the idea of why we're studying this quantity and how it takes the specific form it takes. You have to follow some metaphor and a kind of standard procedure in physics to get this formula. Okay. Yeah, so what I want to point out so there's a specific better formula for, or a nice expression for mass. That's the point of the talk. And so I wanted to point out the following, kind of the best formula for mass, you might say. So in this context, Witten proved the positive mass theorem. And what he did was, he studies some spinors. The most simple ones would be SU2 spinors on a 3 manifold. That's spin 3. And he looks at these spinors, which are kind of asymptotic to some constant spinor at infinity as you travel far away to the end of Euclidean space in the asymptotic chart. Okay, and then what he showed is if you have a Dirac harmonic such spinor, which you can find if scalar curvature is non-negative, then, well, okay, here's a Parker-Taubes paper that people usually read in place of Witten's paper. It gives this expression, which, I mean, in the terminology that we'll be using today, it looks like this, is that this mass of the asymptotically flat Riemannian 3 manifold can be bounded from below by this integral, where this psi here is the Dirac harmonic asymptotically constant spinor. And it's actually equal. I don't know, I shouldn't have put an inequality here. It's equal. This is kind of, I would say, the best formula for mass. Very quantitative and should be used for stability stuff that we like to study, but somehow no one's used it. But this should be the best formula, I would say, but people don't use it. And just to, if you're not familiar with the area, this formula comes from the Leshnerevich formula, which states that when you take, so there's some Dirac operator here that I haven't mentioned, but if you apply that twice to any spinor, that will be like minus the Laplacian of that spinor plus 1/4 scalar curvature times that spinor. It's like a Bachner formula. And then if you integrate this, if you inner product this with the spinor itself and then integrate over the manifold, this is the formula that you get. Okay. So, I mean, I think it's roughly accurate to say people haven't exactly understood what to do with this formula for mass in terms of, for stability questions. So let me move on from this and discuss the formula that I want to get to, which is the one that I was a part of. Witten's proof was in the 90s and 80s. Okay, some of this stuff. So here's just a kind of odds and ends here that I want to mention before we, I get into the bulk of the technicalities. Okay, so first of all, we will need to borrow this idea of exterior region that Christina mentioned in her talk. But I think it was mentioned in the specific context of Schwarzschild space. But in general, there's a notion if you have a general asymptotically flat manifold, like all these conditions above that I'm always pointing at. And actually, in some more general context, this is true. But you can consider a region which you obtain by removing all closed minimal surfaces, all closed, embedded surfaces in your manifold. So here I have drawn some asymptotically flat initial data set, and there might be zillions of little minimal surfaces all around here. Who knows? There's definitely one in this little neck region, wormhole sort of thing. You delete all of these guys, delete all minimal surfaces, terrible set of your asymptotically flat manifold, perhaps. And then you just consider the component which contains the asymptotically flat end after deleting all that stuff, which I've drawn here in purple. And then you take the metric completion of what is left, because that was an open manifold, and then you take the metric completion as it can be closed thing again. And so if you did that in this picture, what would happen is, okay, you'll have one kind of minimal surface here from that one tiny thing that enclosed that little hoop region, and then maybe you would have two new boundary components that came from deleting the one in that neck or that handle that was shown there. Okay, so this would be like a exterior region. I would denote this MX. The point is, well, there's this kind of pretty deep theorem. We don't need to use the real depth of it, but there is a deep theorem of Meek-Simon-Yeah, which says that this region is actually diffeomorphic to the complement of some disjoint balls in Euclidean space. So it really is, as we've pictured here, it's Euclidean space minus some regions that are, bounded by spheres. Okay, maybe I don't need to say any more about that. But this is a notion that we'll borrow later. Okay, so here is the mass formula in the title of the talk. Some of you are familiar, some of you are not. Well, let me just explain. Here's the situation. Okay, we're on our asymptotically flat manifold. Imagine it has one end, it has this exterior region that we're talking about, denoted with mx. On this manifold, you can solve for the following type of function. A function u, which is harmonic, in M exterior region, has Neumann boundary conditions on the boundary of M exterior, on those minimal boundary components. And then at infinity, it is asymptotic to not a constant, but it's kind of asymptotic to one of the asymptotically flat coordinates, one of the coordinates from Rn or R3 that you had from the assumption of being asymptotically flat. So you could say du minus, say, dx pi is big O x to the minus tau. So the function maybe itself is not asymptotic to, if we're fixing some I, fix some I going, some number one between 1, 2, or 3. One of the three asymptotic coordinates at infinity, and you can solve for such a function, not uniquely, but up to an additive constant is unique. Okay, so fix, it doesn't have nothing special about xi, but I want I want it to be asymptotic to some linear function of the asymptotic coordinates, where that linear function has norm 1. So might as well just be one of those dxi's. Okay, so in this setting, then you can find, up to additive constant, there is a harmonic function u with Neumann conditions on the boundary, and asymptotically linear, so that this very nice formula holds. Well, it's not a formula, it's an inequality, but the mass of the manifold is bounded from below by this expression. So it's a little bit strange, but an integral over the bulk of the manifold, the whole exterior region, you have the Hessian of the function, norm squared, divided by the norm gradient, and then plus the norm of the gradient of u times scalar curvature. That's the mass formula. Okay, let me make 2 remarks about it. The most important remark is that there's a positivity theorem here, which is to say that if, in addition to the above, scalar curvature is greater than or equal to 0, then, well, the right-hand side of this inequality is positive, so mass is greater than or equal to 0. And this is known as the positive mass theorem. Okay, so this is like the 5th or the 4th proof of the positive mass theorem that there was, originally back in the 80s, due to Shane Yao, and then, as I pointed out by Whitten, but this is a more recent proof of it. It's a corollary of this inequality.
Can I ask about the theorem statement?
Please.
When you say asymptotic to L, do you mean in C infinity, or?
Sorry, say again?
When you say U is asymptotic to L, what do you mean, like, precisely by being asymptotic?
Oh, very good. Okay. So I wrote it over. It's all scrunched over here. Yeah, I mean that. So L is this expression. It's basically just one of the coordinates, like x1 or x2 or x3. It's one of those. And the asymptotic. So U is asymptotic to L, this statement, means, well, U minus L as you travel out. There's an asymptotic condition as as you travel out into the end of the R3, the chart at infinity. This is big O, including up to 2 derivatives, norm of x to the 1 minus tau.
I see. So like in the right-hand side, you're dividing by the gradient, but like for instance, you don't know like whether the gradient of U is bounded from below.
Right. Yeah. This should, you should feel maybe a little bit worried about this expression on the right-hand side. It's not clear that it's, if there's critical points of the function, your gradient vanishes somewhere. In general, it will need to, just for basic topology reasons. Then, you might be worried that something weird is going on the right-hand side. Nevertheless, this integral is bounded by the mass. So
Okay.
it will be integral. Yeah.
Okay, great. Thank you.
Yeah, I'll go over I'll spend some time on the details of this because it is a little bit strange. I also want to point out that tau is just some number like bigger than a half. So the difference between U and L might not be going to 0, depending on what L is. It won't be going to 0. But what is going to 0 is definitely the differentials, du minus dxi. That thing goes to 0. It's not really very consequential remark, but it's just to clear that up. Okay, and so hopefully on the website we'll post these slides and you can view these links. There's some other work that's has elaborated on this formula. So there's space-time, kind of initial data set version of this fact. There's also a version for when you have a electromagnetic field present. There's another kind of similar formula for not just mass, but mass minus total charge sort of expression. And those stability statements for those kinds of, I didn't even tell you what the rigidity result was. The rigidity is the following. Okay, this is following up down here. If scalar curvature is non-negative, then the mass is non-negative. That follows immediately from this formula. So if the mass is 0 and scalar curvature non-negative, well, this formula immediately tells you that, okay, well, this Hessian sort of thing should be 0. But then you might feel a little bit weird because, okay, I want to say that the Hessian is 0, but not exactly because I'm dividing by the gradient. But asymptotically, if you're way, here's interesting stuff, but way far away, the gradient of U is not 0 for sure, because it's supposed to be asymptotic to a constant, grad xi. So way out at infinity, the gradient doesn't vanish. And at infinity, then you know that the Hessian will have to vanish. And then you could integrate the fact that the gradient is non-zero way out here to then kind of integrate that along a curve into the interior of the manifold. And anyways, you'll end up finding that the Hessian has to be 0. Oh, whoops. What happened? Yeah, the Hessian will have to be 0. Let me not write that. There's not enough room there. Well, it's equal to 0. Okay. And then, as you may know, if you have a gradient vector field, which is killing, its Hessian is 0, the function whose Hessian is 0, then you'll have to split metrically. The Riemannian manifold is split metrically. And if you're asymptotically flat and you split in one way, you got to split in all ways. You have to be flat. So then you are isometric to R3. So that is the rigidity statement of positive mass theorem. let me just write that because that's a part of what the workshop is. If scalar curvature non-negative, mass is equal to 0, then your whole manifold, which you thought might have been very interesting, have lots of topology and geometry, actually it's isometric to flat R3. And I was just explaining how you prove that with this formula. When it's 0, then the Hessian of your harmonic function vanishes, and that gives you splitting. Okay, right, and we're interested in the stability statement. If you almost satisfy the hypothesis of this rigidity statement, you almost satisfy the conclusion. And then what I wanted to point out is these things on the left-hand side. Now here, there are similar rigidity statements for positive other versions of positive mass theorem when you have an electric charge or who knows what. And then those stability questions are unaddressed. That's all I wanted to point out. Less work on those. So maybe if you're interested in getting into this area, these are some questions to consider. Anyway, so let me get into some technicalities here. So I want to explain where the formula comes from. How do you prove the formula? And maybe some tools, and point out some tools of the trade that you might not get from reading the paper necessarily. That's my hope. We'll see if I do that. Okay, so I want to try to now explain how one obtains a formula like that, or inequality for the mass. Okay, yeah, and the key important person here is Daniel Stern, who worked out these ideas that basically the ideas that I'm going to present here is just an elaboration on what he did in the closed 3 manifold setting. And then, of course, I mean, we did this paper together, so he was also working on the positive mass theorem. But all these, all the following tricks and observations, these calculations are due to him, Daniel Stern. It will be at Cornell in the fall. Okay. So to gear up, let's first think that we got some compact region, or let's just look at a compact Riemannian manifold, omega, and it has some boundary. And suppose I got some nice smooth function with no critical points. And I would like to compute some interesting formula. Well, the following is an identity that literally holds in this setting that I've discussed. When you have a compact region omega, some smooth function u with no critical points, then this is literally true. This strange inequality here, which you might say looks quite close to the mass formula. You see the Hessian thing here, you got a scalar curvature times the gradient there, and then you got some extra stuff. Of course, if you're harmonic, then some of these stuff go away, and you look pretty close to the formula I was just presenting for the mass. Okay, so this is kind of, sometimes we call this the master formula, from which you can compute many interesting things. Okay, oh yeah, and here and throughout, I will use sigma t to denote the level sets of u. U will eventually be the harmonic function. I was playing the lead role in the mass formula, and this is well, sigma t will play a large role. Okay, so the calculation starts with, so I'll go quickly, and maybe, all this stuff is kind of written down in many places. First in Daniel Stern's original paper, and then in a lot of papers that I've been involved in. It's been getting a little bit, like the presentation, like little details are added here and there. But let me give like an overview of everything. And if you ever have a question about the validity or the meaning of the inequality, please let me know. I'm happy to explain it because it's kind of been, well, the literature is not perfect about it. But okay, so the idea starts with the following. So do the Bachner formula, except with a bad power. Usually you would compute the Bachner formula involves the Laplacian of the norm of gradient of u squared. But don't do that. Compute the Laplacian of just the norm of the gradient of u to the first power. And why do I say this is a bad power? Well, because this function is not smooth near critical points. So it's not clear what this literally means when you're near a critical point. You know, the function's not differentiable. It's like the absolute value function at the origin. But for the first pass, we'll just assume no critical points. Okay, then you get this nice, well, I mean, it's kind of lengthy, but this kind of expression here using the Bachner formula. Okay, all in terms of second derivatives of the function is the point. I mean, obviously, except for this term, but that will go away. Okay, now what is the trick to obtain, to get scalar curvature into play? You know, obviously here we see Ricci curvature, but I want a formula with scalar curvature in it. And the trick is to use Gauss and Codazzi formulas for a submanifold of our Riemannian manifold omega. So, you know, here we have omega, and inside of here we have, you know, some sigma t level set of u. Imagine it intersects the boundary of omega, why not? And then the observation is that the normal to a level set, well, you can compute that by doing gradient of u over norm gradient of u. That'll be a unit length vector field orthogonal to the level set. And so you can then take a look at the traced Gauss and Codazzi equations, which allow you to express ambient curvature in terms of curvature of a submanifold and the extrinsic curvature of that submanifold. That's what the Gauss-Codazzi allow you to do. And it will allow you to exchange this Ricci curvature that you see up here in terms of some other stuff. Ambient scalar curvature, the Gauss curvature of the level set. I write that with a K. That's Gauss curvature of sigma t. And then extrinsic curvature stuff. Mean curvature is the H, A is second fundamental form. And then notice that you can write extrinsic curvature in terms of the function and its second derivatives. If you haven't seen that before, let me remind you briefly. This is basic Riemannian geometry stuff, but maybe, I don't know. I just decided to include some detail. Why not? Okay, so, you know, like the second fundamental form, you know, I got some submanifold like this. I got two tangential vector fields, X and Y. I want to compute the second fundamental form. Well, it depends on how you like to think about it, but it's either plus or minus the rate of change, you know, kind of the covariant derivative of one of the vector fields in the normal direction, and then paired with that other vector field. I mean, maybe this is roughly this is what one definition for second fundamental form. Okay, but then nu you can think of as well, it is norm grad u over, or sorry, it's the grad u over norm grad u. And then if you you know, do a little swap here and do the product rule, you know, the chain rule here. Oops. So here you get the following two things. So when you compute the gradient, you know, the grad x applied to this quotient, you get on one hand, you get this sort of object, gradient hitting the nabla x hitting grad u. And then you get this other thing, which will be 0 because grad u is orthogonal to the x and the 1. And so, you know, so then, you know, from this calculation, you see that the second fundamental form is equal to the Hessian of u, but restricted to the tangent space of the level set. And so that's the thing that's allowing you to do all this stuff, writing all extrinsic curvature in terms of second derivatives of u. Anyways, you're not supposed to follow along all the calculations here, but this is how, these are the ingredients that you could then use to then integrate and obtain this expression in the top. Okay. So you do that. So you started with computing Laplace norm grad u. Okay, you integrated that on by parts, and then on one side you got something like this. And then the other thing that I want to do is I want to use a Gauss-Bonnet on the Gauss curvature term. So if you recall in the last slide, I had a term that looked like this: norm grad u times Gauss curvature of level set integrated over the whole omega. Or I've written m here, but I meant omega. Well, the co-area formula says this is the same as integrating from the min and max values of u over omega, the integral of Gauss curvature over the level set. And that thing I can use Gauss-Bonnet on. So, and let me remind you that, sigma might have a boundary itself. So I have to use Gauss-Bonnet with boundary, and when doing that, there is a geodesic curvature of the boundary of the level set which I've written over here on the left. And then I also see some integral of Euler characteristic as I use Gauss-Bonnet. Okay, and this is basically the formula. This is like the main thing. So here I've assumed that we're harmonic, and I use these two last tricks, co-area and Gauss-Bonnet. And then I just rearrange that. And this is basically the thing that if you take regions exhausting the asymptotically flat manifold, apply this formula, you get the mass formula that I wrote on like the third slide. Namely, somehow in the correct situation, all of these things tend to mass as the regions exhaust the manifold. Okay, so now there's two things to address. How do those things converge to mass? And then also, how do you deal with the presence of critical points of our function? All right, Christina, did you have a comment?
No, I'm good.
May I ask a question?
Please.
Is there any reason that you would expect the mass to pop out at this point?
Good question. And the answer is absolutely. Because you have scalar curvature here, and you've integrated it by parts. Anytime you can integrate an expression involving scalar curvature by parts, you almost always get mass. Especially if the order of things works out. I mean, the boundary term here is like is like the normal derivative. Just write n of norm grad u integrated over the boundary of some region. Okay, and norm grad u, it's like 1 plus something that's like big O 1 over R roughly. And then when you take a derivative of it, and this depends on the metric G, you basically get something that like something that depends on G 1 over, well, it's like, 1 over R squared after you take a derivative here. And then you're integrating it on a two-dimensional object. So this is like big O1. You've integrated scalar curvature by parts, and on the boundary you have something which is a constant. That constant, you've proved the theorem. I don't know, there's something to check that the boundary term is literally can be identified with mass, but this proves the theorem regardless. So you know that you're doing something.
I see, thank you.
I mean, obviously that's vague, what I said, but that's really how all the experts that I've talked to think. I mean, that's roughly what, yeah, how people literally think about this stuff.
Well, there's also maybe like a separate question of like independent of where that expression came from, that the asymptotics of U do pick up M somehow, right?
Right. What I just said just indicates that it is probably some number. um, yeah.
So to pick up the actual mass, it's important that it's asymptotically linear, is what you're saying.
I mean, it's the norm is asymptotically 1 is important.
Okay.
The mass is going to be contained in the metric. Sorry, that's an important point I didn't really talk about. But the mass is contained in the metric, not the function. I mean, it's contained in the norm of the gradient of the function. So I guess you could say it's a little bit in both. But yeah, the point is it's the right order to pick up the hope to pick up the mass from the metric. Yeah. Okay, let me go over this a little bit briefly. It's a little bit technical and the details are a little bit explained. Let me try to point out, in the papers, let me try to point out something that's not so well explained. But okay, so to deal with critical points, you redo the calculation from scratch and you kind of regularize it, which is to say you put an epsilon somewhere in the calculation so that it literally makes sense when epsilon's positive, and then you try to take a limit as epsilon goes to 0 to get the formula that that makes you a little bit worried, but in the end of the day, it does make sense. Okay, yeah, and the point is that near a critical point of view, even if it's smooth, norm grad U is only Lipschitz in general. And yeah, Daniel introduced the following kind of reasoning. You redo the calculation, but instead of starting with Laplace of norm grad U, you do Laplace of P epsilon, where this is the square root of norm grad U squared plus epsilon. And this function is smooth. If U is smooth, this thing has no problems. So Laplacian of it makes sense on a pointwise level. Okay, so you do that, you introduce an epsilon that way, and you compute something that depends on epsilon, do the same calculation I just talked about. And then you also, in order to help to take the limit as epsilon goes to 0, you break up the range of U. So, I don't know, range of U. Here's U minimum, U maximum. You break that up into 2 pieces. One piece is called A, and that surrounds all the critical points. You have some open set which contains the critical points of or critical values, sorry, of U. And then the complement, which is like a good set, even though it starts with a B for bad, but it's a good set, which is kind of bounded away from where the gradient of U is bounded away from 0. Or rather to say, the pre-image of B under U, on that set, the gradient of U is bounded away from 0. And the idea will be to shrink A so that it has, take the limit and make the measure of A go to 0, which is possible by Sard's theorem, because the collection of critical values is measure 0. Okay, so that's the strategy, is to compute using phi epsilon, also break into good and bad regions to help aid in taking the limit as epsilon goes to 0 and the resulting formulas. Okay, so if you do what I just suggested, you start with phi epsilon and you redo the calculation, you get something like this. So a boundary term is more or less the same as what we saw before. This is kind of similar. It's written in a co-area form. Notice here it's basically the same as before, but it's written in a slightly different way. If epsilon was 0, this would be what I wrote before. And then plus some other stuff where you make some argument and show that the other stuff goes to 0 as epsilon goes to 0 and the measure of A goes to 0. Okay, and then you hope that what you have after you do that, after you take those limits, you will get the formula that I wrote in the beginning. Now there's still some kind of funny business going on here, since I've written this in a co-area kind of way, and as you take B, as you take the measure of A going to 0, it's not clear whether to what extent U inverse of B will approach all of the region omega. So that's kind of a subtlety that's not really addressed in the first papers so much, because in the full theorem you are writing like Hessian of U squared over long grad U over all of omega, not just some iterated integral like this. Anyways, there are ways to compute in a slightly different order and use some limit theorems, like for instance, you can use a monotone convergence theorem on the Hessian part, because that's a non-negative thing, and that as you take regions exhausting all of the omega, this will converge pointwise. Or you can use the limit theorem on that. And the scalar curvature part also can be written as a bulk integral eventually, not just as some iterated integral here. And something that's also sometimes helpful is the critical point set of U, because its solution to elliptic equation has a small measures, Hausdorff codimension at least 2. But depending on, I can't write a general formula that will be very rigorous in every context. It depends a little bit on the boundary conditions. Let me not go into that, but again, volunteer myself if you have any questions about to what extent you can interpret these formulas as, or how they get proven. Okay, so now we have some kind of nice formula like this. I've given some argument for, given some compact set omega, some harmonic function on it, might have critical points, might not. In general, it will. You have a nice integral identity of this variety. And again, the weird things that we want to understand in our context are Euler characteristic and these boundary terms. We want to identify them with mass somehow. Now let's specialize to this situation where we're working on M exterior. And this has the property that, well, this is the only property we need of it, that the exterior region, the homology, second homology relative to its boundary is trivial. It's a R3 minus some balls, has no homology relative to its boundary. Okay, in this context, and we got a U on M exterior, which is harmonic, and it has Neumann boundary conditions. We can do the following. So we can observe that the level sets, the regular level sets, will in fact only have one component and one end. Roughly speaking, these asymptotically linear harmonic functions, their level sets, they might look wobbly, they might have some topology, whatever, but they will be connected and only have one end that looks like R2. So they'll be asymptotically look like planar things, flat planes. Well, how do you see this? Well, okay, yeah. So first of all, one thing that you will want to rule out is that there are no compact connected components of a level set. Because if there were, well, the fact that we have a trivial homology means that there would be some open set omega. Oops. I've already erased it somewhere. There'd be some region omega here, so that its boundary is a level set, and on the inside here, this is some component of the boundary of M exterior, where we have Neumann conditions. And this would violate the maximum principle, because by the Hopf lemma, there can be no max or min of U on this region omega on boundary exterior. That's by Neumann. Because, you know, maximum and minimums of harmonic functions, they got to have strict sign outward normal derivative at their extrema. And then so the maximum and minima have to be on the boundary, but it's constant there. So that would mean that U is constant on this whole omega, but it's not. It's a, you know, it's not a constant function, because asymptotically it's got to be linear. It's not possible. Okay, and actually, and then with a little bit more analysis, you can show that the Euler characteristic of all the level sets has to be less than or equal to 1. That will help deal with this Euler characteristic term. Okay, and then this is the point. So whenever you do positive mass theorem, again, as we were talking about, you have to identify the boundary term with mass. And that always requires some calculation, which maybe I won't go into the full detail just to respect the time. I mean, I'm not going to go into full detail because you don't want me to. Not because it's awful, but because I will fumble the ball on that one. But let me give you a little bit of a hint for why you can believe, why you should be able to deal with the boundary terms, incorporate that with the Euler characteristic and obtain something that you might imagine would be mass. Okay, so we apply that, you take the omegas to be kind of these cylinders, these kind of square cylinders in the asymptotic region, which have height, you know, minus L to L. So that the top I will choose that to be a level set, sigma L of our function U, and the bottom I will choose to be a level set sigma minus L. Okay, so as L is very large, this resembles some kind of planes on the top and the bottom. And then on the sides, in this asymptotic region, I'll choose that to be where the other two asymptotically flat coordinates, have, cylindrical radius L. Okay, so I'm going to apply that formula where I take the domains to be these cylinders. The boundary of the cylinder has a side, a top, and a bottom, and then, of course, the interior boundary of the exterior region that we're working upon. I don't know, let me go quickly here. So on the top of the cylinder, this is kind of like we have Dirichlet conditions. Because U is constant on the top. I mean, it's how we define the top. Okay, and since U is, well, okay, so what's the boundary term there? The relevant boundary term will be the normal derivative of norm grad U. And since we're at a level set there, the gradient of U is only in the normal direction. There's no tangential part to it because it's constant on the top. So you can identify norm, or the normal derivative of norm grad U with the part of the Hessian of U. And then if you want to decompose Laplacian of U along this top part of the cylinder along a level set, you can write that as Laplace on the level set on the top part of U plus mean curvature at the top, norm grad U, and then plus this part of the Hessian. And so, since we're harmonic, and since U is constant on the top, you can interpret this Hessian of U term that we get, it's the boundary term on the top with the mean curvature. And the same goes for the boundary term on the bottom of the cylinder. It's kind of mean curvature information, which kind of has the right order to take an integral of over a two-dimensional object and hope to obtain something like the mass. That's what's going on the top and bottom. Those are the only relative. Those are the only relevant terms in the mass formula for the top and the bottom. Now on the sides, you have kind of a Neumann condition. So you have a almost Neumann condition on the sides, because U is becoming asymptotic to like x1, and that's going to be almost orthogonal to x2, x3. So here the gradient of U is going to be all tangential. And so when we calculate a normal derivative of norm grad U, you get a piece of the second fundamental form, namely the piece of the second fundamental form in the direction of gradient of U, which, I mean, it's like in this direction. You're picking up second fundamental form in that direction. Now, when you incorporate the boundary geodesic curvature of the level set, because that's another term that you have to deal with on the sides, didn't have to deal with it at the top and bottom because those were entirely level sets. They didn't have pieces of the boundary of a level set up there, but you have pieces of boundary of level set on the siding of the cylinder. You also have a geodesic curvature term, and those combine. Those are the two different almost orthogonal pieces of the second fundamental form. They add up to be the mean curvature of the sides, which is good. That's now not going to zero at the same order as the mean curvature of the top and bottom. It's going to zero at a slightly smaller order. In particular, oh yeah, and then, well, let's go down here to wrap up this discussion. We'll use this thing. Yeah, so now we're down here. So the mean curvature of the sides, it's like the mean curvature of a large cylinder in Euclidean space. It's like 1 over L. And also the area of the sides, it's like, well, it's like 4 pi L squared. So this integral of this thing over the entire sides, it's something like, and times 2, because there was a 2 in front of the boundary terms. I'm getting a little bit all over the place here, but I'll finish in a second. If you do that, then you'll get like 8 pi L. Now, 8 pi L is exactly what you get from the Euler characteristic that was integrated from minus L to L, because there was a 4 pi Euler characteristic and the integrated from minus L to L, so that's 2L times 4 pi times Euler characteristic, which is bounded by 1. So anyways, you get 8 pi L. That cancels with the principal part of this boundary thing on the sides of the cylinder. And then the next lower order term turns out to contain a piece of the mass. Okay. This is just the vague outline of how this calculation goes. Again, really only convinces you, this should only convince you that you get some kind of number in the boundary term as you take these omegas exhausting the domain, not that you exactly get mass. But let me stop those technicalities there. And then in the last couple of minutes, I want to make some preliminary remarks on how to use this for stability, or how I was thinking about it for stability. Okay, so here's the formula again for mass from the beginning. What did I have hidden over here? Oh yeah. Oh yeah, this is okay. Let me just say the following. Okay, so we were allowed to take any L, so linear function at infinity. If you take that to be x1 or x2 or x3, you get 3 different functions, harmonic functions, that you have this nice formula for. And so that gives you can combine that into a map to R3. So that each component is satisfying these nice bounds. So from the M exterior to R3, you get this kind of canonical map, unique up to rigid motions and translations to Euclidean space. And so this is maybe a nice map to use to try to compare yourself to Euclidean space. I also want to remark that the leftover Euler characteristic things and the scalar curvature, I've never seen anyone use those to do anything for stability sorts of things. Really only this I've seen being used, this part of the inequality being used for stability statements. That's neither here nor there. So here's the first pass at stability, or the way I was kind of thinking about it. Okay, so we have this weird thing, which is the Hessian squared over norm grad u. Now this bounds not the Hessian of u, really in any sense, but it does bound the L2 norm of the gradient of square root norm grad u.
Oh.
So it controls like the W, you know, as so a weak derivative of the gradient of norm grad u. The kind of directly.
Oh.
Sometimes you call it, you know, Cato inequality, but it's just a basic inequality algebra, you know, matrix inequality, I guess. Okay, so this is the kind of control that you get on the gradient, at least immediately from the mass. No extra assumptions at all. You know, this is just algebra. And then notice you could use a Sobolev inequality. Maybe you work on some compact region omega and use a Sobolev inequality. And if you remember what the powers are, or like W1P in dimension 3, you will get this. You will get a norm grad u minus, or norm grad u squared minus some constant to the 3/2 power. You could write it like this. That will be bounded by mass, because, you know, because it's bounded by that, times some Sobolev constant of omega. That's the subdomain of the asymptotically flat manifold in question. Okay, so this is something you can do. And then, so informally, let me just say, informally, if you're working on a region where the U1, U2, U3, the harmonic functions that are asymptotic to x1, x2, x3 are roughly well behaved, you know, like they're kind of orthogonal, which in a kind of a weak sense, which should follow from the mass formula. On some domains, you could then say something like the following, like the gradient, the pairing of grad ui with grad uj, again, ui is meant to be asymptotic to xi, asymptotically flat coordinate. Then that minus some constants times delta ij, so the 3/2 norm is, loosely speaking, controlled by mass. Wait, sorry, is there a question? Okay. And then the only other thing I wanted to say before I make one more concluding remark is that this is kind of like L3 convergence of the metric tensor. If you think of ui as coordinates, or you're working on a domain where ui are forming coordinates, then this pairing here is like G upper ij. So this statement here that this thing is bounded by mass is kind of like it's loosely like some LP control on the metric tensor, which it's similar to D3 control from like the Manchin-Lee Neumeier Naver paper, which is the as I wrote here, the barely doesn't make sense value. Because when the dimension, when P is equal to the dimension, this doesn't, their metric dP doesn't really make sense, but it just kind of loosely resembles the dP right at the borderline kind of control. So that's how I think of how the mass formula tells you about controlling the metric. But again, subject to some kind of asterisks of like on good regions or on some regions. Okay, and then my other concluding remarks, which I can go quickly over, is okay, so like just some statements that no one else might mention.
Can I ask a question before you leave that
sorry.
slide?
Yeah, go ahead.
So Christina, you write that grad u squared minus a constant, and later you write constant times delta ij. Is there a reason this constant isn't just 1?
Well, it kind of depends on what's Sobolev inequality.
I mean,
I'm
because
thinking,
if the
like
UIs are kind of like XIs, Wouldn't you
Yeah, so
want
I'm
to try to
thinking
get
of,
it close to 1?
yeah, literally what I'm thinking of is the constants are like the average value of grad UI over omega.
Mm-hmm. In both of these cases.
Yeah,
Okay, thanks.
which, I mean, if omega is in the asymptotic region, it would be, as you say, close to just 1 or 0 if I is not equal to j.
Okay, thanks.
This is all kind of informal, so yeah.
No, that's perfect. Yeah.
That's why I brushed over that. Yeah. Yeah, and then just to mention some things that maybe won't appear later in this little workshop. So kind of that reasoning that I just talked about was kind of the impetus behind a paper that Brian Edward and I, Brian Allen, Edward Bryden and I did last year, where we just assumed a little bit more, I mean, a lot bit more, in order to take that that kind of D3/2 control, or that D3 sort of control, and then turn that into an actual theorem. And so we proved the theorem, which says, okay, if you have L3 controls on curvature, and if you have a uniform Sobolev constant of metric balls in your manifold, strong assumptions, not considered totally natural for the full stability conjecture. Well, because you get a much stronger statement. You get actually Holder closeness to Euclidean space. But again, I just wanted to mention that because that's like, I just wanted to make that, we wanted to make this reasoning kind of go through, and we assume a little bit extra when you make it happen.
Right.
The other thing that I wanted to mention, oh, no, don't look at that. So, okay, Marcus Curie, Dan Lee, and I did also a version using a kind of Cheeger-Colding style of argumentation to assume a lower bound on Ricci curvature, and then obtain some kind of Gromov-Hausdorff, pointed Gromov-Hausdorff convergence. And then the other one that I wanted to mention that actually, Christina, you mentioned already, was some of this work that Finster was involved in, Bray-Finster or Finster-Cath, where they actually used the Witten spinor formula. It's all to say that I think these ideas should be revisited. This kind of statement is a bit cumbersome to use, but is interesting. I won't go through it because it's a little bit convoluted. But there was some, yeah, I don't know. I wonder what can be done with with the Witten formula. I think that's a kind of interesting direction to approach. And then I want to end by saying that there's a totally unrelated paper that I want to advertise, which is a paper by Brian Allen, Edward Bryden, and I about a rules theorem, which has a intrinsic flat stability statement for, your rules theorem. If you're interested, I'd be happy to talk more about that. But that's all I want to talk about. All right, thanks for your attention. Sorry, I went over right on that.
Yeah, I just want to thank you for your lovely talk, and open the floor to questions.
Would you say that the level sets of these harmonic functions U might be, I mean, under what circumstances might you say that grad U was say greater than or equal to 1, or
Yeah, that I have no no understanding of. Well, I mean, you can define a set like that. You get like what Kong, Han, and Antoine do. Define some set.
where that's true, right?
Yeah, or where
Okay, so then he'll probably talk about it
have-
tomorrow. Yeah. Okay.
where like norm grad U is like, I don't know, 1 minus tau or something.
Yeah.
And then
Yeah.
at least the mass formula would tell you that the boundary of that set is small. can measure loosely.
Yeah, I see.
There is kind of a strange dichotomy of like, if norm grad U is super big, then this is closer to, well, I mean, not closer, controls the Hessian better. Because, you know, if the bottom is very big, then this is like, then the Hessian's got to get even smaller. So when the gradient is very large, then this mass formula gets stronger. And if like norm grad U small, kind of elliptic estimates kind of better.
Mm-hmm.
That's very loosely. I don't know if there's anything to read into that, but
And what
you know,
about
both ways you get some kind of better control on U. I vaguely feel, but then maybe that's not. Maybe there's nothing to read into there.